Hello students, we are discussing the combination of resistances in an electric circuit. Earlier we have discussed about series combination of resistances. Now we will discuss about parallel combination of resistances. The parallel combination of resistances is seen in our domestic electric circuit. Okay, so the combination used in the domestic purpose, that is a parallel combination. In another video we will discuss the advantages of a parallel combination over series combination. Okay, so now we will discuss some different concept of parallel combination. Now let us see here that first see the definition, that what is called a parallel combination. Okay, so how can we identify a parallel combination? Let us see here first that thing. Okay, see here that when two resistances, two or more, it may be two or more, okay, not only two, it may be 2, 3, 4, whatever. Okay, when two resistances are connected side by side, okay, such that each resistor provides an alternate path for current flow. Okay, alternate path for current flow. Understood? Try to understand this one. Each resistor provides an alternate path for current flow between the endpoints. Okay, see here, this is the source of current, and a battery here. Okay, current is flowing, current I is flowing through this. So what happened here at this juncture, this current that flowing through this gets different path, this path, and this path. Okay, three paths are available for this current to flow. Okay, so that's why it is written here, alternate path for current flow. Okay, so three paths are available here. Now see, between the end points, okay, the resistances are said to be connected in parallel. Such resistances where there are alternate path for the current to flow. Okay, different paths for the current to flow. Such type of resistances are called parallel combination. And in series combination we have seen one path only. In series combination we have seen only one path. Okay, one path is available for the current to flow in the series combination, but here there are different paths are there. These in this diagram there are three paths available. Okay, see here, in other words, when a number of resistances are connected in such a way that they have a common positive terminal, observe here, these three resistances have a common positive terminal. Okay, and in common negative terminal, this is a common negative terminal for all the three resistance, okay, common negative terminal. Then the resistors are said to be connected in parallel. Okay, then so this is an alternate way to define the parallel combination. Okay, so when they have a common positive terminal at one end and at the other end they have a common negative terminal, then also we can say here not. But in this series combination, this is positive terminal, okay, this one is negative terminal, isn't it, with respect to this, isn't it? So this one is negative terminal, this one is positive terminal with respect to this one. Okay, so positive, negative, isn't it? So they don't have a common terminal here in the series combination. Okay, but here they have a common terminal. Okay, positive for all the three resistors, okay, and negative for all the three resistors are same. Okay, so now see here, a potential difference applied across the combination is the same. Okay, try to understand this sentence now. The potential difference applies across the combination is the same as the potential difference across each resistor. Okay, Try to understand this one now. The potential difference, suppose here the potential difference is V, okay, potential difference is V. Now this is see here, this is V, okay. The potential difference across the combination through this, in this combination of 3, the potential difference at this point, the potential difference at this point, potential difference here and here, okay, at these 2 points, this is the potential difference, okay, this is V, okay, this is V here, this is the potential difference. Now this potential, what is said here, now see, potential difference across the combination is the same, this potential difference is the same across each resistance, okay. So for the whole combination, this is the potential difference, and this is same to the potential difference of this first one, to the second one, and to the third one. For all the 3, V is same, okay, because all the 3 are connected at the same point, isn't? This first one is connected here and here, okay, second one is also connected here and here to the same point P and Q, to the same point, the third one is also connected to P and Q, isn't? So whatever is the total potential difference of the circuit, it is same for each of the resistors, all the 3 resistors also have same potential difference, okay. Now try to understand with a different practical situation, an analogy here. Now see here, a combination is given here, the path of flow of water is flowing through this, and this water gets 3 different paths, okay, 3 different paths. Now at this point, the pressure of water at X point, this pressure of water for all the 3 paths is same, isn't it? The pressure of water for all the 3 paths is same, okay. And at Y also the pressure of water is for whatever water comes out, this water flows through this, okay, some water flows through this, some water flows through this, okay, they again come at Y and combine together, okay. That means whatever water coming through this inlet, okay, that water divides in 3 paths, okay. But at the 3 paths, beginning, at the starting of the 3 paths, at the beginning of the 3 paths, the pressure of water is same, okay, pressure of water for all the 3 paths is same here and same here. That means at the beginning and at the ending, the 3 outlets have same pressure of water, okay, same pressure of water, isn't it? So that pressure of water is, here we say potential difference, that pressure of water here is said to be potential difference at the 3, this point, at this point, okay, at this point. So what happened, the pressure of water is like this is same, here the potential difference is same, okay, the same potential difference, okay, the same potential difference, same potential difference, okay, for all the resistors. This is the important thing, okay, potential difference remains same, okay. Now what happened here, the potential difference remains same, but the suppose this current I when flows through this current I gets 3 different paths, okay, this path and this path. Now is that current I that divided into 3 parts, that water goes here, here and here, is the water same in all the 3 pipes? May not be, okay, that may not be, okay. The current flowing through these pipes may not be same, that depends upon what, resistance, that depends upon the individual resistance. They may not be same, they may be different. If these 3 paths are equal, these 3 resistances are equal, R1, R2 and R3, all the 3 are equal, then the total current is divided in three parts, equal parts. Then this total current will be divided in three equal parts. But if they are not same, then in the first part there will be current I1, in the first part there will be current I1. If they are not same, then this, according to the value of resistance, this path will draw the current. Then in the second path also the current will be I2, in the third path also their current will be I3. That means the three paths will get different currents, I1, I2 and I3. Three different currents will be there in the three paths. Why? Because of different resistors, different resistances. Now if they are equal, then this I1, I2 and I3 are same. If this R1 equal to R2 equal to R3, then this I1 equal to I2 equal to I3. Then they are same. Remember this. So this is the parallel combination. Now see what we get now. In the series combination we get same current in the all the resistors. Each of the resistor gets same current. But in parallel combination, what happened? The current is different in different paths. In the series combination, we have what? Different potential difference across each resistor. Potential difference is different in each resistor, but in parallel combination it is same. It is same. In parallel combination it is same. So let us see these characteristics. These are important characteristics here. Now see here, number one, the potential difference for all resistor in parallel remains constant. Remains same. That is, it is same for all the resistor. Remember this thing. The current branches in the inverse ratio of the resistance stances of the resistor. From this it implies that more the resistance of the resistor, less is the current. More is the resistance, more is the value of R, less is I. Less is I. More is the resistance, less is the current. So inversely proportional. The current draws by each path depends upon the resistance. Already I told you. So more is the resistance. If more, then that branch will get less current. If resistance is less, that branch will draw more current. The total amount of current entering or leaving, try to understand this point. The total amount of current entering or leaving the parallel circuit is equal to the sum of total of current flowing in the individual resistor. The total amount of current entering or leaving. Try to understand here. The total amount of current entering. This, suppose from this I current enter. This I current gets three paths. So this total current is I in the circuit. This total current divides into three parts, I1, I2, I3. That means that I is equal to what? I1 plus I2 plus I3. And when it leaves the circuit again, again they combine and become I. Again they combine and become I. So that means what we can say? This one, that I equal to total current is equal to what? I1 plus I2 plus I3. So remember this one. If the I is the total current, if I is the total current entering in parallel circuit, and I1, I2 and I3 are the current in individual resistor, then I equal to I1 plus I2 plus I3. So it is very important result here we get in the parallel combination. In series combination we obtain V equal to V1 plus V2 plus V3, isn't it? In parallel combination we get I equal to I1 plus I2 plus I3. So remember this is a very important result here we obtain. Now see, how can we derive, how can we find the expression for equivalent resistance. Okay, how can we find the equivalent resistance of the circuit? That means what is the total resistance of all the three, okay, of this combination. What is the total resistance? We are finding that now, that expression. How can we find the expression of this net resistance or equivalent resistance of these three resistors? Okay, let us see now. So one important result we get, that what, I equal to I1 plus I2 plus I3. okay, this is the important result we obtain in the parallel combination. So I means we can write, what we can write according to Ohm's law, V equal to IR. okay, so I equal to V by R. okay, so we can write here, isn't it? I means here V remains same for all, isn't V for this, V for this, V for this, V for I3. okay, for all it is V, for all the three it is V same, isn't it? So V by R we can write equal to V by R1 plus V by R2 plus V by R3. okay, isn't it? So in R1 I1 current is there, in R2 I2 current is there, in R3 I3 current is there. So cancelling V, what we get, 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. okay, so this is the important, a very important this relationship we get. okay, the reciprocal of the total resistance, is equal to sum of the reciprocals of the individual resistance, so this is a very important result we obtained in the parallel combination. okay, in series combination it was what, R equal to R1 plus R2 plus R3. okay, in series combination, isn't it? But in parallel it is 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. okay, so remember this. Now we will if we do some numerical problems, then it will be more clear to you. okay.